Hello. Now we're going to talk about the potential energies that we're going to be dealing with. There are various types of potential energy, but we're going to deal with two in particular. One is called gravitational potential energy, and the other is called elastic potential energy. The first, we want to define potential energy in general. Potential energy, is, as opposed to kinetic energy, which is energy in motion, is energy at rest, or think of it as stored energy. Energy waiting to be converted to kinetic energy, or waiting to be used. Now, the two that we're going to talk about, the first one is called gravitational potential energy. And this is simply elevating objects. When I talk about doing work on a marker, moving it from here to here, I absolutely did work on this marker, and I absolutely added energy. Specifically, I added gravitational potential energy. Now, gravitational potential energy has a formula. And I use PE sub G to denote gravitational potential energy, and it's mass times gravity times height. Mass times gravity should be familiar. That's the weight of an object. Remember, weight we also call gravitational force. So basically, that's that force, and height is just a vertical distance. So if we think back to work, work was force times distance. Guess what? This is too, a force times the distance. So that's how we can also end up in joules. So to calculate the increase or decrease of gravitational potential energy of an object, you take its weight, and however far it moved up or down. Up is positive, down is negative. So if you elevated an object, say 2 meters, the object weighed 300 newtons. 300 newtons times 2 meters gives you 600 joules of potential energy that you added to that object. So gravitational, pretty easy, pretty straightforward. The other one to look at is called elastic potential energy. And elastic potential energy has to do with stretching or compressing objects. Every material has elasticity. Some have more elasticity than others. For instance, a spring can stretch or compress, but yet a brick can't necessarily do that. A brick is pretty rigid, but technically it can stretch or compress its molecules. So when we look at the formula for elastic potential energy, it is 1/2 kx squared. Now, the K is what we call the spring constant. We're just called a spring constant, but it really has to do with all materials, not just springs. So any material has its own spring constant, it's just a number. In other words, a spring in a ballpoint pen is not the same as a spring in your car. I mean, they serve the same purpose, but you can't take the spring out of a pen and put it in a car and vice versa. Now, the unit for the spring constant is newtons per meter. All the different differences between those springs go into making the number with the unit. In other words, the thickness of the spring, the length of the spring, the material, the density, the elasticity, all those factors go in to make a number. All right? Likewise, x. X is a distance that the material is either stretched or compressed from its equilibrium position. The equilibrium position is where it is at rest. So say that the object is 1 meter in length, and before you stretch it, now it's 3 meters in length. X would be 2 meters, the difference between where it was when it was at rest to where it was when you stretched it. Likewise, if it was 1 meter in length and you compress it to say 3/4 of a meter, 0.75 meters, then X would be 0.25 meters. That's how much you compressed it. The unit for X is always meters for the formula that we have to use here. So again, the two different types of potential energy we're working with, gravitational, which is mass times gravity times height, and elastic potential energy, which is 1/2 kx squared, where k is your spring constant, and x is the distance that's either stretched or compressed from equilibrium. Go.